Welcome learners to the course on Quantum Electronics Part 2. Myself Orpon Deashi from the Department of Electronics and Communication Engineering from RCC Institute of Information Technology, Kolkata, India. Welcome you all to my lecture 8 of the series of lectures on quantum electronics. Today we start to discuss about the absorption coefficient calculation in bulk and quantum well structure. The total calculation of absorption coefficient and corresponding implementation of oscillator strength is typically subdivided in two lectures, lecture 8 and 9. Today, in lecture 8, we will discuss about the interband transition, and in the next day, we will go for the inter-subband transition. So today we start with the concept of the absorption coefficient for bulk and quantum structures, precisely the quantum well devices, and we will call the interband transition for our discussion. So far, in the last 7 lectures, if you can recall, we have discussed about the foundations of quantum electronics, the application of Schrödinger equation along with the boundary condition in quantum well structure, the solution of Schrödinger's equation with appropriate boundary condition in order to determine electronic properties, precisely transmission coefficient, eigenstates, and later calculation of density of states. In transmission coefficient calculation, we have shown that two easier numerical processes which can be solved by hand, and we have applied them in our lecture 3 and lecture 4. In lecture 3, we have applied the transfer matrix technique. Lecture 4, we have applied propagation matrix method, and then we have incorporated the specific band structure calculation, that is the band non-parabolicity factor, and showed how realistic material parameters really affect the electronic properties of the device. Later we have calculated the quantum Hall resistance, and now we are going for the optoelectronic properties, precisely absorption coefficient and oscillator strength. So today, before going to the mathematical calculation, let me start very briefly what absorption coefficient is. So I have started with a very simple structure which you have probably encountered in your childhood life of science book or physics book, where you know the reflection and refraction properties of light, or better to say an electromagnetic wave, when it is incident at the interface of two media. Two media means they are different in terms of refractive indices. So I have started with the same notation, and I am saying that if naturally an electromagnetic wave comes, some part will be reflected and some part will be refracted. So naturally the refracted part we can consider it as absorbed in the second medium. And we have considered the already it's covered in our lower level physics book, the Beer-Lambert's law, that intensity is a function of distance and it is a function of I0, which is actually the intensity at the interface, into e to the power minus alpha z, where alpha is the absorption coefficient. So these are our known expressions previously, and we can just adopt it so far as our primary level knowledge is concerned. And why I have started with this diagram, because just to make you familiar that we are not going to make something novel, something very big, innovative, no, not at all. It's a very basic level physics of reflection and refraction of light, and light is an electromagnetic wave. So naturally we can consider and start with this known expression, and naturally you can adopt the Beer-Lambert's law in the structure. Basically, yeah, Beer-Lambert's law is actually originated for the structure, so it's fine. We have no problem with that. Now, if we start to consider the absorption coefficient calculation or the absorption process, absorption process of 4 types in bulk semiconductor and of 2 types in quantum well. So in next 6 slides from this onwards, what I will try to discuss this absorption coefficient calculation. Obviously, I will go for calculation, but what are the physics of different processes and how the carriers are moved from one band to another band or one energy level to another energy level, those sort of things. We will try to illustrate for each specific case. We will try to illustrate and will show that these are the optical absorption processes in different type of structures. And once these things will be clear for all of us, naturally we can proceed for the mathematical derivation, which is very simple, but I will explain the steps which are integrated for every point of this. And then I will go for the quantum well structure and just modify the derived equation for a bulk structure, and then we will try to calculate that for a quantum well structure, so for the same optical processes. Now, for absorption coefficient or for absorption process, when we will define it for a bulk structure, naturally the first process we will consider, that is a band to band. Now, what band to band means? It means that electron in valence band, which I am showing with a light blue color circle, which is electrons in the valence band, they can absorb a photon. The photon is incident on it. I think you can visualize it. It can absorb the photon with enough energy. Now, what do you mean by the term enough energy? Enough energy means the energy of the photon should be such that it is almost equivalent to the band gap of the semiconductor. So if that is absorbed, then by absorbing it, it is excited to the conduction band, and naturally it leaves a hole in the valence band. So I am showing hole as a pink circle in the valence band, and our primary electron, which we have considered, which is previously at the valence band, now goes to the conduction band. And simple, it is a band to band transition, or more precisely it's a valence band to conduction band transition. Naturally, absorption means you have to absorb the external energy, and naturally so the electrons will go in the higher up and holes will go to the lower up. So that means it's nothing but the absorption process, that energy is increased. So it goes from more negative value to less negative value as per the band diagram is concerned. So this is nothing but a band to band absorption process. The next point is the band to exciton. Now, as per our concept, this process and the previous process means the band to band process, are almost exactly same with a very minute difference. So before going to the text, let me first explain the diagram clearly so that you will be able to find out that what is the difference between band to exciton and band to band, and that will really help you to understand that how exciton is formed. And when we will later go for the Frenkel pair and all those things, then different types of exciton and the application of Schrodinger equation in exciton, whether it is bulk structure or a quantum structure, and then you will find the binding energy of the exciton and everything in the details. But that's a distant process, so let confine ourselves in this absorption process, which is band to exciton. Let's consider the same electron in the valence band, give a photon of energy almost h nu, and it goes to the conduction band. So it's simple, but this newly formed hole in the valence band and the electron which is in the conduction band, if they form a pair, they form a pair means they form a pair due to the Coulombic interaction between themselves, and then it will be called as a exciton. And in that case, please remind the matter that the magnitude of the Coulombic attractive force between the hole and electron critically depends on the relative permittivity of the material, that means the semiconductor concerned. Now, what is the difference? If they form a exciton, then this sort of thing is nothing but a protium 1H1. So this is called band to exciton absorption process. The previous case, what is the difference? Let me point out very briefly. If you consider a band to band transition with a band to exciton transition, for band to band both the carriers are free. The electron and hole both are free. Whereas for band to exciton, it's bounded. So I think you can get very easily the concept that band to band and band to exciton, the difference. So band to band, these are things are free, and band to exciton, I think it's a bounded thing, so everybody knows it. So what is the difference? That if a exciton moves, both the carriers will move with a mutual dependency. But for the free carrier, that means for band to band transition, they will also move, but they will be mutually independent. And that's the major significant difference between the band to band and band to excitonic transition. And that we should remember once we will go to the chapter of exciton. That will be probably in lecture 12 and 13. If time permits, then I will go for that. And that's the basic difference. Next comes to the third process, which is called band to impurity or impurity to band. Now, normally in a semiconductor, doped semiconductor, the impurity level will exist at the forbidden region. That means though the region is forbidden, but in a particular energy level, the carriers can stay. So, if you have a electron in valence band and absorbs the photon, then naturally it will go to the impurity level, which is the closest possible level available for it, and naturally it will go to the impurity level. Or otherwise, if some atoms exist, some carriers actually exist in the impurity level, which is shown in the right side picture, by absorbing the external photon, it can go to the conduction band. So what you will find that by means of the appropriate photon, an electron can go from valence band to impurity level or impurity level to conduction band, and that deals with the absorption of process in the bulk semiconductor for band to impurity or impurity to band. I think the terminology is quite clear because based on the process, the term will be preferred, whether it is band to impurity or impurity to band. Naturally, for current conduction, you require impurity to band, but for liberation of the carriers from the valence band, you require band to impurity. And that's the significance of this type of structure. Next, I am coming to the free carrier. What is free carrier? That an electron, when it absorbs a photon, goes to higher energy level inside the conduction band, or the hole which is stay in the valence band absorbs a photon and goes to the energy level, that hole, inside the valence band. That means free carrier, when I am considering the term, it's intraband transition for bulk. Naturally, it will go from one energy level to another energy level. Now, you may give a question that these energy levels are very close. Yes, obviously. For a bulk semiconductors, the spacing between the energy levels in the conduction band are very, very close. But for quantum structure, it really matters. So this is basically, that's why if it is very close, then the carriers can be considered almost free, and that's why it is called free carrier absorption. So all total, we will get 4 different absorption processes in bulk semiconductor. First one is band to band. Second one is band to impurity or impurity to band. One is band to exciton. And fourth is the free carrier, that means the intraband for bulk semiconductor. Naturally, if we move to the quantum well process, I am just enlarging in order to make it view proper, so that I am going to now quantum well. For quantum well, there are two types. One is called intraband, another is called interband. And one point at this juncture, I may just help you to remind that this intraband transition, sometimes also referred as inter-subband transition. The term is same. Intraband means inside the band, and naturally it is inter-subband, which also means inside the band. Now for intraband, consider the electron at the lower energy level, and by absorbing the photon it will go to the higher energy level, and that's nothing but the interband transition. So that means inside the conduction band. Similarly, it may happen inside the valence band also, but I will consider the fact later. Whereas for interband transition in the quantum well, you will find a key factor that it can't be a transition from top of valence to bottom of conduction, because at least there is half h cross omega energy difference due to the harmonic oscillator principle calculation. And naturally for interband, if you consider the hole in the highest occupied level in the valence band, then by giving energy it can be transferred to the lowest occupied level of the conduction band, and this energy transfer depends on the naturally the band gap and more than the band gap, because this transfer will be greater than the band gap. So that's very very important for interband transition, and naturally people can get more levels, energy levels in the valence band, because of the valence band probably splitting in some cases, so spin orbit split off and heavy hole and light hole formation, so different matters take place, and naturally you will get some different data for some same interband transition if you consider the realistic band structure and other factors. Now with this very small introduction, that means different things I have discussed, different processes for bulk as well as for quantum well. Next I am going to the mathematical calculation for a bulk semiconductor for interband. Now I have written again the same equation at first, that is di dz equals to I into alpha with a negative sign. Naturally negative means you know that in a solid material if electromagnetic wave propagates and it will die down. So negative sign is nothing but that indication. And what is alpha? Alpha is the absorption coefficient, everybody knows it. So what will be the energy absorption? That is also defined. Before going to that, let me say what is the rate of energy absorption. So rate of energy absorption is nothing but area into Dij. And since it is absorption, so it will be loss of energy, so that a negative sign will come. And if you substitute Dij from the previous expression, it will be A into I into dz into alpha omega. So it's nothing but a simple trivial mathematical calculation for the interband transition. Now energy absorption, that is also defined as h cross omega into T. Now what is capital T? This parameter is very important. Capital T means you have to consider the total transition probability. And what is total transition probability? It transition probability from valence band to conduction band naturally, and h cross omega is the energy of a single photon. So that is the energy absorption, that is the definition of the energy absorption. So if you equate both the sides, then area multiplied by intensity multiplied by dz into alpha, that is h cross omega t. So you can very easily find out the value of alpha, which is h cross omega transition by ai into dz. So it's a very simple calculation and you will get the value of alpha. The question is, what is I? I is a very looking its intensity. Naturally we don't look after the intensity too much, but intensity is also function of the frequency and also the function of refractive index. Look at the equation. Now there is a term nr. Nr is the real part of the refractive index. We don't take the imaginary part. So I is a function of n and omega. And why? Because n is the real part, is also not a constant quantity. N will vary from wavelength spectra to wavelength spectra for a particular material, and that's why omega square into nr, this total function, is a trivially a frequency dependent parameter for this bulk semiconductor. And there are some other parameters, the amplitude of the electromagnetic wave, because that's also required. So this is the value of the intensity we have considered. So if you substitute the value of intensity, naturally it will become 2 mu 0 c h cross omega t vc by this. And if you substitute, if you take a into dz, cross section into length, naturally it will become volume. So I have made a into dz as volume, and then I will get the value of the alpha omega, and I have substituted mu 0 c equals to 1 by c epsilon 0. So naturally I am going for the permittivity, and you may ask why you are going for permittivity instead of permeability. The answer is very simple, because we have to deal with the exciton, and once you have to deal with the exciton, naturally you require the electrical permittivity, the relative permittivity of the materials. So transition probability of an electron from valence to conduction band, that's given by this bracket vector. You know that kv and kc are the wave vectors applied to the Hamiltonian, and naturally you have to take the square, because you know that for power calculation we know that amplitude should be squared up and multiplied by the delta function. And what is now delta function? It's very significant now on. You are transferring the electron from valence to conduction. Naturally you are making a transfer from valence band wave vector to conduction band wave vector. That's the difference, and it is of the order of h cross omega. So naturally when h cross omega equals to ekc minus ekv, delta function will become 1, and you will get the transmission transition probability, and that comes from the Feynman diagram. I am not going into the details of the Feynman diagram. Later, if time permits, we can discuss in a 10-15 minutes slot of classes. But with that, after calculation, the Hamiltonian will come in this format, and there is a term m square. The m square is a very critical parameter, and which basically gives the transfer of the momentum from valence to conduction band, and it has a fixed numerical value for every material. So if you search the handbook of the semiconductor physics or devices, you will find that m. So what will be the total transition probability? Naturally, we will incorporate the Fermi-Dirac statistics, and that's why it will be Fermi function of valence band multiplied by 1 minus Fermi of conduction band. And why it is 1 minus, you know that valence band is filled and conduction band is empty. So naturally, we have to take in this manner. And the function 2 is, as usual, you have to incorporate the Pauli spin degeneracy factor. So I have multiplied it by 2. And if you substitute, and so you will get the transition probability for a single electron. So for all the electrons you have to integrate it, and where you will integrate, naturally you will integrate on the Fermi sphere. That means you have to integrate on d cube k, and this delta function integral d cube k, it's a very simple calculation. You can incorporate several functions, you will get the result. So the result is given here. It will be 2 pi into 2m star by h cross square whole to the power 3 by 2 into root over h cross omega minus eg. You may ask what is MR. MR is the reduced effective mass. I think this parametric value is known to all, so it's not a matter of concern, but it is ultimately the reduced effective mass. And so you will get the total transition probability, which is q square v by 8 pi square h cross m0 square into the amplitude square into m square. M square is the momentum matrix, and multiplied by the function which comes from the integral of the delta function. So what will be the absorption coefficient? Naturally you have to substitute the value of transition probability, and you will get an expression, and the graphical variation is given below. Naturally you will find that it's a band to band, so you can't make very high energy. It will just help him to escape from the band, and that's not possible. So our absorption coefficient will increase with the energy, but after some time it becomes almost constant, and that's the requirement of the absorption coefficient. So we have just calculated absorption coefficient for bulk material, and naturally most of the significant derivation steps are given. If you go to the more, you can go for the textbook of Omar Manares. It's an excellent textbook. It deals with the detailed calculation of the Poynting vector from where other factors are calculated, and that's Maxwell's equation solution. So everything is given. You may refer to that book in order to understand it more vividly. Next comes to the absorption coefficient in quantum well for interband transition, and naturally quantum well means there are no continuous energy levels. So the effective mass or the density of states will be reduced. So if reduced density of states will be given in this form. Now there may be several questions. I will expect that GVM and GCN are what? GVM and GCN are the overlap functions integral. Naturally the functions will overlap, and they will be somehow naturally overlapping function, and that will give you the effective value. It's the cross section of the common cross section of the both the functions that will give an purely value. So these factors are required, multiplied by the so Heaviside step function. And why we have considered the Heaviside step function, you know that if h cross omega equals to ENM, naturally the electron can go from valence to conduction band, and that's one of the very important factor. And what is ENM? It is the band gap plus conduction band offset plus valence band offset. And so capital L will be called the width of the quantum well, and we know what will be the value of ENM. So at that time it's given in some different aspect, but end of the day ENM is very important because it ultimately gives you the concept of the shift or the half harmonic oscillator, which is half h cross omega, and that's why the bands are not merged with the conduction or valence. That means the energy levels are not merged with the conduction band bottom or valence band top. So naturally we have to consider these additional factors, and ultimately we will get the value of alpha omega, and alpha omega is given in this format. So this is the absorption coefficient in quantum well for interband transition. And if you consider the oscillator strength, what is the oscillator strength? That's a very important question at this time. Oscillator strength is nothing but it gives the probability of transition from one quantum well to another quantum well. And naturally, if you calculate your oscillator strength 2m square by m0 h cross omega, which is for a quantum well, then if you substitute, you will get the modified expression of the absorption coefficient. So absorption coefficient and oscillator strength are parallel to or proportional to each other, better to say, sorry, it's proportional to each other, and more oscillator strength means more absorption is possible for that quantum well. So these are some selected reference. As usual, I have said the Omar Manares textbook, and this is the MIT, the link where some details of the absorption processes are given. You may check this also for your ready references. And that's all for today. So in the next class, I will go for inter-subband transition in the quantum well, and I will also incorporate the oscillator strength again for that derivation also. Thank you all for